We have two wonderful talks to look forward to now, and the first one is to be given by Woosok Moon from Nordic.
Thank you very much for inviting me. So today, I know this session is about sea ice, but I'm going to talk about El Nino right now. But I have to say that this research is inspired by sea ice, even though I'm going to talk about the tropics. Okay, so generally I'm going to talk about the seasonal variability. So I use the El Nino as an example. So, and then I'm going to introduce some time series analysis method. Okay, for example, in climate research, monthly average data is kind of a basic data set. So for example is Arctic sea ice extent. It is original data from the satellite, and then from 1979 for 30 years, you can see the up and down and then slight change. And then actually, we want to talk about the sea ice melting due to global warming, whatever. However, in this original data, actually, it is very hard to see that change because there is one major cycle here. That's the seasonal cycle, right? There is a clear seasonal cycle in this data, but what we want to see is some long-term change or long-term update of this seasonal cycle. And to see that, normally in climate science, we erase the climatological mean seasonal cycle. It's very simple. We just average 30 years and then take out from the original data. That is the result. And then here, we can see a clear sign of some decline of the Arctic sea ice during around the 30 years, and then we blame global warming. That's the common procedure when dealing with some climatology data, especially monthly mean average data. So in the case, I really want to ask that, do we really erase the seasonality from the data? So because we erase the major cycle through some averaging method, still seasonality always remain even in the variability after erasing that seasonal cycle. It is another domain of Arctic sea ice extent. I collected 30 the seasonal cycle of the Arctic sea ice extent, and then this one is from January to December, and then you can see maybe we can refer that this band size is kind of a size of the variability. And then if you look at this band size, as time goes by, it is different. For example, in the summer, it seems to be big. During the winter, it seems to be small. Still, variability also has a seasonality, even though we erase the climatological mean season cycle out of the data. So the question is how to present the seasonal cycle of the variability in some model. What is the methodology? Okay, let's motivate some problem, research problem. Normally, okay, I'm going to use some surface temperature. That's the basic indicator of the climate. In the case, think about it. For example, some in the middle latitude area, the seasonal cycle of the temperature, it could be 30 degrees, right? The summer, 25 degrees, and winter could be -5, -10, even though it is different from UK weather, but normally, so quite a bit. Actually, that is normally controlled by shortwave radiance, right? That's the biggest energy flux. If I just write down the major physics of that, that might be the surface energy flux balance. This term is temperature change, and then I collected a surface energy flux balance, and then I divided it by time scales. The first one, I'm going to call it seasonal forcing. As you know, seasonally, normally, mainly, shortwave radiance is going to change it. And the second term, I just want to say weather. Very fluctuating. So here, I just want to use the noise term. And then the magnitude of the noise is going to be different depending on the season. And then the last one, very slowly varying some energy flux, which might be from ocean or global warming. And then, after dividing up some prefactors, the temperature evolution equation looks like this one. And then this model should represent original data. This is surface temperature for northern hemisphere average and southern hemisphere average. Original data has a clear seasonal cycle right here. And then from this model, from this data, we normally erase a climatological mean seasonal cycle. And then I argue that climatological mean seasonal cycle T bar satisfies this mean equation. And then the remaining this fluctuation, which is represented by x, and then x is much smaller than this T bar. And then I want to use some Taylor expansion of the Q around the climatological mean seasonal cycle. I want to call it AT. That's also a periodic function. In the case that the evolution of the x represented by this one. In the case that there is a first ATX term, it might represent the stability of the system, right? Depending on the sign of the A. And second term represent weather as noise term. And the last one, small f, represent additional long-term flux, right? I'm arguing that this model might represent this fluctuation quite well. That's just my hope right now. So, I mean, to motivate the research, I just, because it is a CIS session, so I have to make an example about the CIS. So, I just show some example about the stability. Normally, for example, if you just make a CIS thermodynamics model, some seasonal model, we have to put a lot of forcings. The most important one is also shortwave radiance. So in the case, mathematically, that if we just collect all of the flux, it represents like some f. And then this small f is a periodic function, right? The period is 1 year. And then I argue that there is some seasonal cycle xx. This x is just to think CIS thickness. And then if I want to see the stability of the xs, I have to trace some small fluctuation around xx. In the case, the evolution equation represented by like that. Here, AT is defined by some first Taylor expansion term around the xx. So actually, if you look at this, the reference papers, this paper suggests some exact model. If I just find AT out of some simple RTCIS model, AT sometimes represented like that. This one is the black line shows the AT. Here, if you look at it, the winter AT is negative and summer AT is positive. AT positive means exponentially growing. AT is negative means exponentially decaying. Actually, it represents, if it is positive, it represents there is some positive feedback in there. If it is negative, negative feedback is going on here. In Arctic sea ice, we know that what that is. In summer, there is a famous feedback, sea ice albedo feedback. We put the perturbation into the sea ice, that perturbation grow, that is represented by positive AT. And in winter, ice grow. In the case, a stabilizing process is going on. That is called a long wave stabilization, because the heat is losing out of an outgoing long wave radiance. And then these two processes are competing each other. Eventually, the stability is stable. Because of that, Arctic sea ice is not going to go on quite soon. It stays as it is, even though it is changing. So the next question is, okay, in Arctic sea ice, during the summer, it is unstable. During the winter, it is stable. What is the relationship between this stability information and variability? Right? That is the next question. So to answer that question, I want to put the weather effect, some noise effect. So I want to put some noise term right here. It represents short time processes. And this one is a stochastic model, stochastic differential equation. And because this one is white noise, I want to argue that. And the solution is Gaussian. The Gaussian, whose mean is 0. The whole solution is going to be represented by standard deviation, variance. Analytic solution exists. It is represented like that. And then this one shows the degree of the variability of Arctic sea ice in this model. So it's a little bit complicated, so I want to use our common sense to explain about what is the meaning of this expression. I mean, think about it just simply. During the winter, sea ice is stable. During the summer, sea ice is unstable. And then we are just forcing the sea ice by noise every time. In the case, if we just push the sea ice during the winter, sea ice is quite stable, so sea ice always wants to find the original position. So in the case, the size of the response should be quite small, right? However, during the summer, it's reverse, very unstable. So if I just push that system, because the system is unstable, response is quite big. So because of that, we can expect that the response size is much bigger. So if we think about the seasonal cycle of the variability of the Arctic sea ice, summer is big and winter is small. And then we can see that, wow, there is a seasonal cycle of this variability. And to understand it exactly, we have to go to the next step. Okay, there is a maximum of the variability during the summer. There is a minimum of the sea ice variability during the winter. Next question is exactly when. If we could answer that question, I understand that mathematical solution completely, right, qualitatively. Okay, let's do this process. This is a summer, system is unstable. This is winter, system is stable. And in summer, we are going to generate some response of the Arctic sea ice by stochastic forcing. That response is going to magnify because the system is unstable. Until when? Until the end of the summer, right? Here, A is always a positive, response is going to be magnified exponentially. And then all of the response is going to be magnified until the end of the summer. This transition point, AT is changing sign from positive to negative. Until this point, response is going to be always amplified, and then we are going to sum all of this up. That's the final size of the variance. Winter is reverse. All of the response is going to be decay. Until when? Until another transition point from negative to positive. That is the end of the winter. So we can say that, okay, there is a maximum of the variance during the summer. Exactly when? At the end of the summer. There is a minimum of the variance during the winter. Exactly at the end of the winter. Actually, this is the final solution, that mathematical expression. As you see, the variance is a standard deviation is maximized at the end of the summer, is minimized at the end of the winter. If you look at just the data, Arctic sea ice, seasonal cycle of Arctic sea ice extend. Look at it, just simply, winter is minimized, and at the end of the summer, the variance seems to be maximized. So that simple stochastic model qualitatively represents this situation. Okay, so everybody is clear about the laws here? I hope so. I'm going to use this one again to explain other phenomena in climate. So in the case,
what was that thing you plotted on the right? You said it's extent or it's...
this one?
Yeah.
This one is the seasonal cycle of the, I think, this one is, it's the effective depth of the Arctic sea ice. It is from the biomass data. So we have extent, we have the volume from the biomass data, and then calculate the effective depth.
It's thicker in the summer because...
Yes. So I just used the Arctic sea ice as an example. However, this laws could be quite generalized to any kind of a situation in climate, right? Because the structure is the same, even though physics are quite different. What I mean is mathematical structure should be same. So I'm arguing that maybe climate data or climate system might be represented by three component combinations. One, monthly stability, represented by AT, and then stochasticity, that noise term, NT and white noise term, representing weather. And then, even though in Arctic sea ice example I didn't input this one, but in our climate generally, some slowly varying forcing exists, which is due to ocean dynamics or global warming, whatever. In the case, our question is, if we have monthly average data, like a temperature data, can we construct AT and noise intensity NT and slowly varying forcing FT out of the one-time series? That's some mathematical question, right? I want to say that's possible. So I'm not going to go into the detail of this mathematics. I just want to explain the methodology. If somebody wants to know more about it after the presentation, find me. Okay. So I'm going to explain that methodology. So if you have some monthly average data, after erasing climatological mean seasonal cycle, that's the data we are going to use. First, calculate the second moment every month, the January and February, and then you can find 12 values. Here, the important thing is don't erase any trend or linear trend or whatever, just to use original data, even though there is a trend. I'm going to find it later, okay? Just to use the original data and then find the second moment. And then there is another term, AT. It is a correlation between two adjusted months, some January, February, March, something like that. It also has 12 values. And then the BT is, if you have a January time series, you shift 1 year, and then you can find a lagged correlation, right? 1 year lagged correlation. In the case that you can find the 12 values of the BT. And then I want to define PT, something like that. And then this PT satisfies these differential equations. You can solve it because we already construct SAB already. You can find the P. By the definition of the P, the dP over dt is equal to AP plus 1. So these two right sides should be same. So because we already know the P, we can construct AT out of these equations. After finding AT, everything is very simple. We can construct a new data set, YT, like this one. In the case, based on the model assumption, YT consists of noise term and long term, long first term. And then n square also could be found. These simple equations, some monthly second moment and adjust the month correlation. And then after finding A and AT and NT, the remaining is F tau. So every month we are going to find the remaining. But by the assumption, F is a slowly varying forcing. So I want to pick up the one average value per year. I don't need monthly values for F tau. So anyway, so if I apply this method to surface temperature data, let's see how it looks. I use GIS as a surface area temperature data. This one is just the northern hemisphere, southern hemisphere average, and global average data. So this one is AT for this one is northern hemisphere, this one is southern hemisphere, the black one is global. And then B is NT, and then C is that F tau. And then I put this information, AT, NT, and F tau, and then I can run it, right? Simply every time just to put the noise number, the random number, and then run it. This is the comparison between the model and the original data. The blue one, it is behind anyway. That's the original data. And then red one, it is the model. Model is just simply this equation. Where is it? This equation. Model means this equation. I put all of the information and then run it stochastically. And then if you look at it, so I mean the match is quite good. And then if I just compare, power spectrums, blue is original data, and then red is model. And then this one is a comparison of monthly statistics. Blue is original data, red is this model. This model seems to catch up the most important thing in the data. I mean, the statistics of the monthly average data, right? So this method is working. And then I find monthly stability information and then monthly noise intensity and F tau. I can apply this method at each point of the data. So, I mean, I don't have to rely on some average data, some specially averaged data. So this GIS data has a pointwise, the grid set. I can apply this method every point, and then I can construct the AT, NT, and F tau at each point of the world, right? I want to show that result. I use two data sets. One is GISS data. The other is NOAA SSD data. And at each point, I construct AT. This one is March, this one is May, this one is August, this one is September. Actually, I don't have to explain. I mean, everybody could see that something is going on in some specific area. That area is here, here, here. Where is it? It's the Eastern Pacific. In that case, I have to go to the El Niño talk, right? It is ENSO. So it represents the seasonal stability of the ENSO, right? And then strangely, think about it here, in ENSO area, 80 is negative. But here, August and September, 80 is positive. I mean, think about it. Think about Arctic sea ice case. And then this ENSO case. Very similar. I want to call it two-season characteristic. A is a changing sign seasonally. So actually, for the ENSO, if I use a Nino 3 index, and then if I construct the AT and NT, AT is positive from, I think, July to, I think, November. And the rest of the, rest of the time, AT is negative. And then this one is comparison between model and the data, the monthly standard deviation. It matches really well. What I want to say is, think about the stochastic solution I explained for sea ice. So A is positive for the ENSO case. This is July and some winter. And then rest of the time, A is negative. In that case, the variance is going to be maximized this transition point, minimized this transition point. For the ENSO, this transition point, the maximum variance happens near the winter, November to December, right? And then this one is late spring. Okay, and then this one represents late spring and December. And also, I would just want to show that this time series method works really well for other tropical climate index, Atlantic Nino and Indian dipole oscillation. Anyway, so in that case, what can we explain about the ENSO? So normally, El Niño and La Niña happens during the winter, right? And that name comes from that timing. Even though ENSO dynamics has some interannual oscillation, the period is 2 and 7 years, but whatever, if we would like to see the El Niño or La Niña, the winter is the most possible time, right? That is called phase locking, seasonal phase locking. So this El Niño and La Niña always prefer winter. Why? So, okay, I want to change some question like that. So in the ENSO, El Niño and La Niña means some abnormal situation. So outline of this statistics. So the phase locking question is like that. Why such an abnormal situation prefer specific time of the year, winter, right? And this question is strongly related to why there is a seasonal maximum of the variance of the ENSO near the end of the year, right? These two questions are closely linked. And then the last one, I already explained. Because ENSO, the seasonal stability, change the sign, and then positive from July to at the end of the year. And then all of the signal is magnified and then deposited at the end of the year. Because of that, we are going to see weird situation near the winter. I think that's the simplest explanation about the phase locking of the ENSO. Okay? So second topic is in the ENSO, I mean, it is also related to Arctic sea ice case, some predictability barrier. In ENSO case, if you want to do some seasonal prediction, you are going to run this model. And then what happens is from the spring, the model starts to deviate a lot from the observation data from the spring. So, or there is a value, some persistent. The persistence drops quickly during the spring. It is called spring, ENSO the spring predictability barrier. So always model starts to deviate from the observation from early spring. Why? Right? I mean, it always happens regardless of the model, which means there might be some intrinsic physical characteristic of the ENSO to generate that error, right? Because it happens regardless of the model. So I want to explain that based on this argument. Yeah? For example, to explain about the phase locking, I use the stability. In this case, we have to focus on the noise intensity. I want to focus on the early spring. This one is March, April, and May. Look at the size of the NT. This, some high frequency process intensity starts to grow in Eastern Pacific. Okay? So in the spring, some weather effect is quite strong. I mean, think about the model simulation. Whatever model you guys have, whatever GCM, it's very hard to simulate weather-related phenomena, right? It's hard. I'm not saying it is impossible. I'm saying it is hard, very challenging. So in this, during this early spring, it is possible to generate an error, right? Compared to other times in the spring, because of the high intensity of the high frequency processor, it is likely to generate an error. And then, what is waiting? This unstable time period is waiting for this error, right? In this time period, from July to December, the state is unstable. That error size is going to be amplified, right? And then after that, right after this, amplifier, observation and model might have a huge deviation. This deviation cannot be recovered, right? There is no reason to be recovered. I think that is the essence of a spring predictability barrier of the answer. I mean, Arctic sea ice has the same thing. Arctic sea ice, for example, at the start of the summer, if the error size is big, I mean, we are going to lose the predictability at the end of the summer. Same thing. Okay, so it's almost time, so I want to summarize this one. So I introduced some stochastic model right here. Some seasonal stability exists in this term, and then some seasonal noise intensity right here. And then sometimes A shows a two-season characteristic. Some time period A is positive, the other time A is negative. In the case, at the entrance of this amplifier, there exists a predictability barrier. At the exit, there is a phase locking. That's what I want to say. So it is quite general, regardless of any phenomena. So I used the Arctic sea ice as an example, and the next I used ENSO as another example. So, okay, I want to conclude that. Actually, it is not the first time to introduce this kind of a stochastic model. Initially, 1976, Hasselmann introduced this stochastic model, which is called the Ornstein-Uhlenbeck process. Here, some stability factor and noise. Here, lambda is constant, n is constant. And the solution of this stochastic model represents red noise spectrum. And then here, he could explain why the SST shows in a red noise spectrum. So this model is useful to explain this one. So physics is like that. Some big Brownian particles slowly moving, and then a lot of small Brownian particles interacting with these big particles. In the case, what is the statistical characteristic of this big Brownian particle? That might represent by these equations: stability and then noise forcing. So now here, I just generalized that model. Instead of the constant lambda, I just use a periodic function. Instead of the constant n, I use a periodic function of the n. In the case of advantage, I could generate the seasonal variability of some phenomena, and then I could explain about the simple essence of a phase locking, predictability, and also persistent. So this time series method could be useful, and this form of stochastic model could be very useful in climate science. Thank you very much.
Thank you. We have time.
That's a really neat framework. So you use this method to diagnose the sign of A at different times of the year. Positive indicates times when an initial perturbation will be amplified. Negative, it will be dampened. I think we might have some guess as to what's going on in the Arctic in that regard, but do you have some insight into the physical mechanism of the coupled ocean atmosphere system in the tropics that produces that?
You want to find some physical, the fact what's going to happen in the tropics. Okay.
There's no explanation for the sign of A.
Yeah. That's a good question. Actually, from this analysis, we cannot guess the physical process. It is just to provide the information of the seasonal stability. But if there is some previous research about stability, in the case it is very useful because we can find some strong link between this time series analysis result and known physics. For example, Arctic sea ice is very clear. That during the summer, if we could construct AT and then AT is positive during the summer, we can guess that that is definitely due to sea ice elevator feedback. In the answer, it is positive over there during some time of the year. That is a Bjorknes feedback. So Bjorknes feedback, that is the air-sea interaction process. So normally, it just suggests a simple logic. So trade wind is intensified, and then that is interact with the upwelling of the the ocean, and then that is both generated positive feedback. It has seasonality. That's the physics of this AT. And this research did not suggest a new thing. Actually, previously, the Fei Jin in University of Hawaii suggested this concept using his stochastic recharge model. It's a little bit complicated than this model, and then he suggested seasonal change of the stability, Bjorknes feedback stability, might be the reason for phase locking. And then that model is two-dimensional model. They just simulated it, but they couldn't suggest a very clear physical explanation. But here, same information contained in this model, except 2 or 7 year interannual the variability. This model cannot represent that one, but this model contains the same information about the seasonal variability of the answer. So here, I suggest that some during some time, all of the signal is magnified and deposited at the that transition point, and then I'm just suggesting that's the essence of the phase locking. So,
time for one more, I think. Yeah.
So I'm going to talk. The first half. One question. So, with this idea that the albedo feedback causes the sort of variance of the anomalies to be larger in the summer than the winter, you'd expect that same process to apply in the southern hemisphere, right? Do you see that in the observations in the southern hemisphere?
yes, still southern hemisphere, that's the seasonal ice, right? Southern hemisphere Arctic sea ice. You mean the southern hemisphere sea ice? Yeah. It's sea ice albedo feedback is going on, but sometimes open ocean is exposed during the summer, right? In the case, the degree of the variability might be different. So it's a little bit hard to answer that question quite clearly, but I think there might be some difference because this example I used, it is not seasonal ice. I used some permanent ice state. So if it is a seasonal, it might be a little bit different. But still, there should be some time period for some positive feedback, but maybe timing might be different. That's my guess.